everyone. Thanks for the introduction, Tim. I'm Jaswanth. I'll be talking about Parallel JavaScript. Before I tell you more about it, why Parallel JavaScript? Well, simple. The hardware you have is getting more and more parallel. You have more and more cores on your processors. You have wider vector units. Your GPUs are increasing in performance rapidly. Since 2006, there's been a 75x increase in performance of Intel GPUs. And there's abundant client-side parallelism that JavaScript applications don't use today. At the same time, the kinds of applications you would write with JavaScript has changed. Now you have physics and fluid simulations, you have path tracing, real-time game engines. At the same time, JavaScript programs have access to device sensors, onboard sensors, multimedia streams. So the kinds of applications are changing. They're becoming more sophisticated, more compute intensive, right? But there's no support for parallel computing. But why do we want to invent a new parallel programming model? Why? There are already so many people have invented so many. Why don't we just take one and bolt it on top of JavaScript, right? So it turns out that the web has specific requirements that make this approach kind of undesirable. First thing we want to preserve is ease of use. So this, whatever parallel programming model we introduce should fit in well with the rest of JavaScript. So the programmer shouldn't have to have two different mental models, one for the sequential parts of the program and another for the parallel parts of the program. It should all just be JavaScript. We want to have a very high-level API. We don't want the programmer to worry about compare and exchange primitives or atomic intrinsics or even threads, right? We want to have a very high-level API and fitting with the ethos of JavaScript. And we want to be deterministic where possible. This is hard for parallel programming in general, but determinism is awesome for debugging and deployment, so we want to preserve that. We also want to be platform independent. We want to run on all kinds of platforms, from single-core mobile phones to the most powerful desktop computer. And we also want to leverage different kinds of parallelism on these platforms. So it could be multi-core parallelism, GPU parallelism, or SIMD parallelism. Not just that, we want the programmer to write the same code for all of these different kinds of parallelism. In other words, we don't want the programmer to write one kind of code for multi-core CPUs, another one for GPUs, and so on. We want that to be abstracted away. Our goal is to extract reasonable performance from parallel hardware. Extracting all performance out of parallel hardware is a secondary goal, and this should not be completely up to the developer. The browser runtime should share a lot of this burden of extracting performance. So we want to make the expression of parallelism easy, but not necessarily how you actually implement it. Finally, we want to make it suitable for the open web. We want to, we don't want to increase the attack surface for JavaScript. In other words, we don't want native execution of native code, for example. We still want to preserve the kind of the sandboxed execution environment of JavaScript, right? So this is a brief overview of the Parallel JavaScript API. It's built on 3 pillars. The first is collections. These collections in JavaScript are just JavaScript arrays and typed objects, which are going to be in ES7. Then you have high-level data parallel methods that operate on these collections. Some of these may already be familiar to you, right? Map, reduce, filter, scatter. The par suffix simply conveys the programmer's intention that he would like this method call to operate in parallel, right? It may not, as we will see, but he would like it to be. So very high level, no threads. The third component is elemental functions. These are just regular JavaScript functions that are the things that are executed in parallel across cores, on GPUs, and so on. But there's one important caveat. They have to be side effect free. That is, they cannot alter global state. So a global state may, for example, be a global variable, right? In a parallel region, you cannot, in an elemental function, you cannot change global state, right? You can read it, but you cannot write to it. There are also more subtle kinds of side effects in JavaScript programs, which are engine-level side effects, right? So, for example, just concatenating 2 strings, even though it appears at a surface level as a side effect-free operation, has engine-level side effects. Okay? But it's not up to the programmer to worry about those things, right? It's up to the browser runtime to worry about that. So let's look at some code examples. This is a very simple example of how you would use the map par. You have a tiny array, 1, 2, 3, 4, and then you just give map par an elemental function, which is that fat arrow function over there, and it increments each element in the input array. So this looks exactly like map, right? If you just wrote this using map, it would look exactly the same. The difference here is the elemental function is executed in parallel for each element in this array. So of course, in this case, you don't need parallelism because it's only 4 elements. But if you have 1,000,000 elements and your elemental function is doing something more sophisticated, you can imagine how this would be useful, right? Reduce looks very similar. You give it, again, a elemental function that takes 2 values and returns 1 value. So you're reducing A and B to produce A plus B. And when applied to this array, it produces 10. This is exactly the semantics of reduce that normal JavaScript reduce as well, right? So just by adding par, you're making it parallel, right? However, there's an important caveat here. Determinism, when you do a reduce, determinism is guaranteed only when the elemental function is associative, right? If the elemental function is not associative, then you will transparently get sequential execution. So it'll be equivalent to just reduce. So in other words, the programmer does the best job he can to write code that is parallelism friendly. If not, he will just, if it's not parallelism friendly, he will just transparently get sequential execution, right? Without changing any code. So let's say you have an input image, which is a 3-dimensional width times height times 4, right? 4 is RGB alpha. This is how you would convert it into grayscale. You just do a map par, ignore the 2 over there, and you would just give it an elemental function that averages the first 3 channels, the RGB values, and returns an array with this. So this is a simple averaging grayscale operation. The 2 here is the depth at which you want this map par to operate. So if you have a 3-dimensional collection, sometimes you would like to operate on rows of an image. Sometimes you would like to operate on pixels in an image, and so on. Sometimes you would even like to operate on individual channels, color channels in an image. So the depth parameter allows you to kind of select what slice you want to do this parallel operation on in an input collection. Okay? So you don't have to worry about all the details. You can read the document later, but just to give you an idea of what the API looks like. So reversing an array, a simple example, you create an array using the build par API. In parallel, it constructs an array of length 4 that just contains 0, 1, 2, 3. And scatter par takes a function that maps elements in the input array to indices in the output array. So in this case, scatter par is just taking the first element, putting it in the last index, and so on, right? Filter works exactly the same way as filter par works exactly the same way as JavaScript filter. It's identical. You just give it an elemental function that returns a Boolean, and that Boolean decides whether the value stays in the output array or not. Typed objects are a new proposal for ECMAScript 7. I believe there is a preliminary implementation in Firefox. And the API just works on typed objects identically to JavaScript objects. So it's the exact same grayscale operation that I showed you earlier. It's very similar, except instead of returning a JavaScript array, you're returning a new typed object. Okay? So this is what I mean by fitting in with the rest of JavaScript, right? You don't want to introduce new types. You don't want to introduce new kind of concepts. You want to kind of build upon what is already there. Parallel JavaScript is a ES7 proposal at this point. We're discussing the API in the committee and with browser vendors. There's a specification that you can look at. And a preliminary implementation is in Firefox Nightly. And the API that I've just shown you is kind of is the result of a collaboration between my team and the Mozilla team that is implementing PJS in Nightly. So in order to get parallel execution, they had to solve several challenges. I'll briefly describe them. The first was Jit Support. So for parallelism, you want to guarantee side effect freedom. How do you guarantee that things don't mutate global state, right? The way they do this is they have a static safety analysis that inspects your JavaScript and figures out whether there is a violation of the side effect freedom requirement. They also have right guards, which are dynamic checks that check whether you're following the rule. They have a pretty cool work stealing scheduler that tries to schedule work onto hardware threads in a way that reduces imbalance among threads. So basically, it tries to keep all of your hardware threads. So if you have hyper-threading, you have many hardware threads. It tries to keep all of them busy. And there's a new garbage collection scheme just for parallel JavaScript that is kind of integrated with the SpiderMonkey, Firefox's generational garbage collector. And the cool thing about this is that it actually exploits the programming model, the property of the programming model, which is that you can't have side effects. And this fact makes garbage collection fast, turns out, which is cool. And finally, there's a lot of work on providing detailed reasons for why something did not execute in parallel. So for example, in the map par example that I showed earlier, if I were to insert some DOM operation, for example, which is not side effect free, then the program will bail out of parallel execution and you will just get sequential execution. But your console will tell you that this is the operation at this line number in your program. That is the reason for you not getting parallel speedups, right? They also provide complete stack frames at bailout points so that you can actually debug why things didn't run in parallel. This is really important. Finally, I would like to take a few minutes to talk about parallel JavaScript on GPUs. GPUs are a hugely important resource that I think we should use more in JavaScript programs in the non-graphical portions of JavaScript programs. So I mean a GPU, general purpose GPU programming context. But compiling parallel JavaScript to GPUs is not easy, it's challenging. So I'll kind of outline a few reasons why. The GPUs typically have a separate address space than the CPU. So your JavaScript heap, which is sitting on the CPU, right? How do you make that available to a JavaScript program running on the GPU? You have to copy it, which would be hugely expensive. But otherwise, you would have to map it somehow. So this is a non-trivial problem. Also, even though in some new chips, physical memory is shared, virtual memory is not shared, right? So this makes the problem of mapping non-contiguous parts of your heap to the device very, very challenging. Then there are a number of paths to the actual GPU hardware. There's DirectX, there's GLSL shaders, there are OpenCL kernels, and I'm sure there are tons more. Each of these has slightly different semantics, and each of these allows a different subset of JavaScript. So I'm talking about compiling JavaScript to one of these, right? So as you can imagine, you can compile a different subset of JavaScript to each of these. So you have to kind of reconcile all of these things together in your browser runtime. So some things that would be possible to express in, let's say, OpenCL would not be possible to express in OpenGL, right? Just because of the programming model. So you have to kind of keep that in mind when you're compiling. Then there is no dynamic allocation on most GPUs. There is no notion of a heap as such. It's just scratchpad memory. The star there indicates that on kind of more recent GPUs, there is actually, I think CUDA 2.0 has malloc, but it's not widely implemented on all GPUs. Forget heap, there is no general notion of a stack either, right, on a GPU. So most interesting JavaScript programs would like to do heap allocations, I presume. So this would be kind of hard to support. So you would have to build a dynamic memory manager and a collector that runs completely on the GPU. There are also no function pointers in most GPU programming models. This makes things like Dynamic dispatch, difficult to implement. And polymorphism is also difficult to implement. And finally, getting performance is not always easy. The developer has to kind of keep track of different families of GPUs. Okay, this is a 4th generation GPU with this OpenCL and so on. And this is a CUDA GPU with this version of CUDA and so on. So this is, it's an intractable problem, and it's unreasonable to expect the programmer to kind of keep track of all of these things. So our approach is to basically take this high-level specification in PJS and let the browser runtime figure all the browser runtime has perfect knowledge of what the platform is, right? It can query GPU capabilities. It can do all of that. So the idea is to just let the browser runtime do it transparently. So we have actually implemented a backend that takes your JavaScript and compiles it to run on GPU, and we've implemented it within Firefox. So this is an overview of what it looks like. So the blue parts are just what would happen with normal parallel JavaScript execution on the CPU. So you would run for a little while in the interpreter and the baseline JIT, and once your code has been hit a few times, it's hot, and you know all the type information, then you would go to the IronMonkey JIT, which would spend more time trying to optimize your code. It is at this point that you would do your parallel safety analysis, that is, checking whether something is actually safe to run in parallel or not, right? After that, you would just lower it a few times, and then you would just get native code, right? In the GPU case, we take MIR, which is the mid-level intermediate representation of JavaScript in IronMonkey, and we do GPU-specific safety analysis. So this basically checks whether all the bytecodes in your JavaScript program can be supported on the GPU. So for example, if you're compiling to GLSL, then maybe some particular bytecodes are not supported, right? There are no equivalents in GLSL for some JavaScript bytecode, right? Then we do some simple type inference. This is basically taking the JIT, IronMonkey JIT's type information and translating it into types that OpenCL understands. And we do some optimizations for exploiting local memory, which is very fast on GPUs. And then finally, we just generate OpenCL. And then this OpenCL is built into a GPU binary, and we cache that binary and reuse that binary whenever as long as type information doesn't change, as the types flowing through your JavaScript program don't change, this kernel is valid, and we just keep reusing it. So what does all of this buy us, right? Let's look at the energy and let's look at performance first versus parallel execution on a CPU, right? So remember, the baseline here is parallel JavaScript execution on a CPU, which is already, depending on how many cores you have, which is already faster than regular sequential JavaScript, right? So the blue axis, the blue y-axis is performance relative to parallel execution on CPU. So these are some simple benchmarks that I picked. We have more. I can show them to you later. So this MM is dense matrix multiply. It does 8 times better on the GPU than on parallel CPU. So this is written in JavaScript using PJS, right? And 2D convolution, which you use for things like image sharpening or finding contours or optical flow or things like that. 2D convolution is a fairly important algorithm. That does 2.8 times faster on GPU than on parallel CPU. And Mandelbrot is a simple, you all know the Mandelbrot set. It does 6.2 times better in terms of performance than CPU. What about energy? So for dense matrix multiply, GPU execution is 7.7 times lower in energy than CPU execution, than parallel CPU execution. Similarly, 2D convolution is 3 times, and Mandelbrot is 7.7 times lower. So not only are you getting huge increases in performance from parallel execution on GPU over what is already pretty fast, parallel CPU, right? You're also, at the same time, getting huge decreases in total energy consumption, right? This is big. So just for reference, the matrix multiply program, I believe, runs compared to sequential JavaScript, the CPU version runs 22 times faster. So this 8x is over that, right, on GPU. So that's just to give you an idea. 2D convolution is probably like 6 times faster than sequential JavaScript, and this would be 2.8 times faster than that. OK, let me quickly show you a quick demo. This is a simple program. So there are a bunch of bugs, and the goal of the game is to move them using my hand to the frog, feed them to the frog, or take them to their house, right? So I probably should be standing closer. So it's doing optical flow on the image stream captured by the camera to basically figure out which way I'm moving. So you can see all the bugs settling on my face. So it basically detects changes in energy in the image. So if I were to just run the sequential version of this today, it would run like this. Right? This is pretty slow. Let's go back to the parallel version. So let me go back to my presentation. I can show this to you in more detail if you're interested. OK, so the implementation is in Firefox Nightly. There is a ECMAScript proposal. We would very much like your feedback. This is the time to kind of influence what the API looks like and how it is specified. So if you have any comments, please write to me or just participate in the discussion on ES Discuss and try it out and let us know what you think. Thank you.